without further ado, hello, we are the Space Laddies, and welcome to our presentation of the ingress-egress system for tall lunar structures. Today, you'll be hearing from myself, Collins Davis, and my colleagues, Allison Clark, Jacob Breidenbecker, Donna Coyle, and Tyler Swearingen.
The agenda today, we will start with the overall problem that we came up with, and that a lot of landers that are going to the moon have probably tried to solve in the past. We will go over our initial designs, how we got to the current designs we have, and things like that. Then we will go over our prototyping and testing phase of each of our subsystems. We'll show you how we iterated our design, and we will then go over future works, and then we will conclude.
So the ingress-egress system for lunar landers has been a challenge from the beginning. Here we have the Apollo lander, some famous pictures of Buzz Aldrin descending and Neil Armstrong training to get on the first rung of that ladder. And so the beauty of a ladder is that it's simple, reliable, lightweight. However, it's difficult to use. There's no buddy system. So if another astronaut is injured, it's difficult to get them back into the lander. Or if there's a tear in a spacesuit or some other emergency, that makes the ladder a less viable option. Also, there's the inability to carry equipment up and down this ladder. So you have to access the equipment from another way. These we have some design concepts that if you look on the right, you can see a mock-up of the Apollo missions with an astronaut dangling from a pulley. That was actually one of our first design considerations too. Why don't we just use a simple pulley? But there's a reason why Apollo didn't use it either. And another pulley system would be on what the Blue Origin lander is using here in this artist rendition. This was a concept that was used for equipment, but could also possibly lift humans. We came up with with our own design strategy. So some of the constraints that we considered had to do with load requirements. We wanted to be able to lift 2 astronauts. Each astronaut would be 200 pounds. And then we heard from Sarah that each spacesuit is about 300 pounds. So we took that into consideration when designing for the load. We also considered the whole weight of our entire system, along with the payload space inside the launch vehicle and the moon environment with temperatures of negative 280 degrees Fahrenheit to 260 degrees Fahrenheit. Also, the possibility of landing on uneven terrain.
So we went through and we came up with what we needed to build, or need statements. The human factors that we came up with was that we wanted the system to be safe, intuitive, and could have a larger capacity than just climbing up a ladder or just having enough space for 1 astronaut. We wanted it to be intuitive because we don't want to have a very complex system. We could just have arrows pointing up and down, causing the system to go up and down. The structure, we wanted to be strong and lightweight. We wanted to use targeted weight reduction to make sure that we're not having more weight than we need, as well as using exotic, strong, and lightweight materials to make sure it won't cost so much to get into the space. We also, in terms of operations, we want it to be very steady. We want there to be an emergency stop, multiple redundancies, and quicker ascent, descent than just climbing up and down a ladder.
We went through several design initial ideas where we talked about everything from a hinged ladder that an astronaut could ride up as it collapsed. Then we talked about a linear induction motor system to bring it up, and even a ridiculous spring catapult. But we ended up on an elevator-like system with a winch pulling a platform.
So the concept that we landed on is similar to an elevator. However, the main design focuses are on weight reduction in this case, and it is something that will only be a semi-permanent infrastructure at this point. It's a basic system that will have a chamber that that gives the structural stability for the whole system, with that holds the winch that is then connected to the top hat, which is distributing the load down to the platform, and which is guided by the guidance system to reduce the translation of the and sway. It is designed to hold large equipment up to 453 kilograms, and the design is also compact and storable for transit and launch.
We've divided our overall system into several subsystems as described in the previous slide, where we each tackled one of them individually to have the most efficient approach to this design.
My subsystem I worked on was the winch. The winch is the powertrain of our lift system. Whatever it looks like, it needs to give power so that we can bring the astronauts up and down from the lander without them having to physically use their own effort. We need it to be reliable. We need so that way it works all the time. It needs to be simple so that way they can fix it and there's less stuff to go wrong. And we want to reduce the load that it has to carry. In other words, we don't want it to have to lift itself. Had to go through several calculations in order to spec out everything. Those are all listed there, and they are still ongoing to iterate and optimize everything. The whole system is going to feature gear train ratio using worm gears. They provide a good gear ratio in a very small area. They also provide inherent safety with one-way torque transfer. We want to add a backup crank, so that way if something goes wrong, you can attach a crank to, say, the motor shaft or directly onto the spool and wind it up manually. But if everything is tightly sealed, then it's not likely things should go wrong. The windows on the cupola on the space station are a great example. Material selection is pretty early in this, but we have a few parts like the spool, the frame, primary shaft, and the primary gear that are seeing all of the load. And so those will need to be a very strong, probably titanium alloy. We'll need a different material for the worms, so that way things don't gall and they can slide. I printed a small prototype, which tested gear alignment. That yes, we need two different materials for the worms and the gears. The gear ratio is so high that we'll need a very high-speed motor, and we'll need something to make sure that the cable winds up evenly. Future considerations will include optimizing the gearbox frame, make it smaller, make it lighter weight, run FEA optimization on pretty much everything in order to reduce material where we don't need it. Build some sort of a winding guide. This would probably be like a lead screw or something to direct the cable onto the spool more consistently. And a secondary locking mechanism in case something happens on the primary shaft between the spool and the cable.
This is the chamber. So the chamber design requirements included safety during loading and unloading, structural stability, security and compact during flight. Also that the material would be lightweight as possible, and that we would meet the width requirements of being inside the launch vehicle. So the chamber design was broken down into 5 categories. We have the A-frame, which has it was shaped like an A to optimize the load distribution. It has rounded corners to prevent stress concentration. And it is shaped so that there's more mass on the side that as a counterweight to stay on the balcony, what we're calling the balcony of the lander. The deck has a ramp for safety, and it also has more mass on the side of the balcony as well to act as a counterweight. The crossbar at the top there, that's holding the winch. And we have a safety bar on the outside of the chamber we can imagine that in a bulky spacesuit, when you're loading equipment, you might not be able to see where the edge is. So that's why we have that bar there. And then also the slide rails at the bottom. So this concept would be that in order to be compact during space flight and to keep the chamber inside the launch vehicle diameter, we would have it so that it would be partially stored on top of the balcony. And then when the astronauts are ready for their first egress, they can push it out and it would lock into place so that the platform would be able to lower. We are still performing some analysis. We've done some load calculations on the crossbar, including finding the maximum bending moment and stress, and the maximum deflection, which as the bar is designed now, it would be less than 2 centimeters. So we will keep working to confirm that, and we will do more load calculations. Also, we will perform some FEA. The prototype, we have begun construction on our prototype. We have this A-frame so far, and the purpose of the prototype will be to demonstrate that how the system works, how it would be pushed out. And further testing would include a lot on the slide rails. We're concerned about the stresses on those, and also how they would lock. And also we would be performing some static load tests to get a comparison of what this structure would be able to handle.
And for our system of what we are calling the top hat is our method of translating a single cable into an equal load onto the platform. The main design considerations for the top hat were stability and to keep the platform one level, and two to keep it from translating from side to side. It also needed to be lightweight and compact, and so the final material selections are in the future. But the main design, as far as lightweight at this point, is the use of a T-beam like structure with the vertical supports to support the vertical loads, and the horizontal supports to support or to keep the individual arms from swaying. In the initial prototype and testing, we printed a 1/20th scale and performed stability testing with that. It was obvious very early on that with just the 4 cables hanging down, that there was a huge lack in stability. Putting cross cables on either side of the platform did reduce the translation significantly. However, it did cut off access to the platform for the equipment and astronauts. So in the 1/10 scale, we'll be looking at different cable configurations in order to continue to reduce the translation enough for the guidance system.
The next subsystem to consider is the platform. I started this by assuming a broad material, creating a structure, and iterating. The main design considerations to start with was something lightweight, something that can operate in our appropriate temperatures, as well as maintain sufficient strength and stiffness that it will not overly deflect under load, and it will not yield. In looking at some materials, we were able to eliminate several materials due to their inability to operate between negative 170 and 230 degrees Celsius. We eliminated beryllium alloys due to their inherent problems, including excessive cost and the fact that 50% of people who come in contact with it, they experience toxicity and can even die. Nickel and ferrous alloys were eliminated due to their high weight. And that left us with three main groups to consider. Looking at our main groups of titanium, aluminum, and magnesium, we used other criterion to narrow down to one specific alloy from each group that matched a very well-rounded selection based on our criteria. Those are seen here with some important values. Ultimately, we decided to carry the titanium alloy through the rest of the design because it is the stiffest and strongest, albeit heaviest. The next step was to look at a basic structure. Keeping in mind that we wanted a minimum weight while being able to support the load, a honeycomb structure was chosen due to their known ability to handle high loads with minimal material. On top of the honeycomb structure, we wanted as much empty space as possible. So a 150 millimeter radius circle was chosen as the base shape for our hexagons. That shape allows for minimal material, while at the same time not sacrificing stiffness and not being too big that one might step through the hole. We looked at short-term and long-term possibilities for the platform. The long-term one will be explained in a few slides. In the future, we have a high-level FEA optimization to make the platform the absolute lowest weight it can be while being able to do its job successfully. If this project is to continue on, this step is imperative. Here we can see some FEA results for the platform under a worst-case loading scenario. This would be if one astronaut was injured and the other was carrying them, perhaps on their back. This has all of the load of both astronauts and their suits concentrated on a small area at one point in the platform, representing a foot stepping on. This model had to be simplified due to limited resources and time, but it yielded a factor of safety of 1.7 with a maximum deflection of 16 millimeters using the titanium alloy. Given that this is a worst case scenario, the 1.7 factor of safety is acceptable, even though our design goal is 2. Looking at standard loading, we see deflection, which is much less, and we also see a much higher factor of safety, showing that this is indeed a safe system. Here we can see an isometric view of the short-term life platform to be made from titanium. It will be very light and it will get the job done on the moon. We can also look at a more long-term version where this is significantly heavier, although it is also stiffer and made from aluminum. This is something that can support higher loads and could potentially be used on other missions, such as a Mars mission. Some quick FEA looking at standard loading conditions proves out what I just said, that this is much stronger, while at the same time experiencing less deflection for more long-term or heavier loading scenarios. As far as testing for the platform goes, we have completed an initial stability test, which showed that when we have a slight angle to our cables going up to the top hat, which is not seen in this image, we have decent stability when placing a 2-pound hammer at various locations across the platform. The platform would not slant at all. However, it did sway excessively. With that in mind, a guide at the bottom is crucial. Some upcoming tests include a deflection and strength test on a titanium specimen, as well as some integrated functionality with our 1/10 prototype, as well as our full prototype.
The final subsystem is the guidance. The guidance system is designed to keep the platform from moving when we don't want it to. This is the first design of the railroad up here seen in just a rough sketch. After prototyping and testing, I came up with a new iteration. This is more similar to the final design here, as you can see in the upper right-hand corner. Made in my second iteration after creating and testing my first design, as you can see here in my hand, this is called the Wasig wheel. I came up with a smaller and more robust design that had shoulders in it that will better hold the bearings in place. I also increased the distance between here, the distance on the spool itself. I also came up with where most of the forces will be translated through, and I found that it would be translated through the bearing. So I went with a bearing selection that would be able to handle all those transverse loads. I came up with the fit for the bearings, which would be on the outer, it would be a friction fit, and the inner would be a slip fit. Next, I designed the shaft that would be connecting my guidance system to the platform. The shaft has a shoulder that will press on the outer side of the bearing. The inner side of the bearing, sorry. That rotates. That doesn't rotate, that's static. And then on the other side, it will hold together on using a nut. I also took calculations and found the worst case scenario, a very rough estimation of what the shaft would be feeling. So here is my final wheel prototype, zoomed in for you. So what I have completed on the guidance system, I found the load stress points and found new ways to improve the wheel. My upcoming will be the connector first prototype, the second wheel iteration test, and I will be talking with Collins about how we are going to connect the platform to the guidance system, and I will be making a more specific material selection.
The user interface will be a simple button panel accessible both to the users on the platform itself and at the top of the rocket. It just needs to have a couple buttons to move the platform up and down, as well as an emergency stop to connect or disconnect the power. They also need to be able to find these buttons in a low visibility situation. The buttons are simply going to complete a circuit if you're holding down the button, and disconnect the circuit if you're not holding down the button for maximum safety and control. And then the emergency stop will also disconnect the power. The future work will be attaching our parts together. We'll be figuring out how to store the guidance system and the platform in flight. We'll try and optimize the winch location if it's going to go on top of the chamber, perhaps in the rocket. We'll optimize the crossbar design on the chamber to figure out how to reduce loads on it. We'll also figure out the slide rails for that, how to get it to extend and compress back when in flight. The full prototype we will be assembling, and then we'll complete our full-scale prototype and test that.
In future work, we can see this project expanding in functionality. For example, what if we had the platform to be detachable and connected to an LRV trailer? Or what if we could incorporate a forced gas system for regolith mitigation on the chamber, so that as astronauts are coming up into the lander, they can remove a lot of that pesky moon dust. Also, it would be great if we could have a system for tool and emergency kit storage, along with counterweights, manually powered, a redundancy system for the winch, along with making our system, designing our system for other missions such as Mars.
Risk points that we're looking at is how to detach the platform if we are just unable to get the thing to move. The forced gas system that was mentioned, we'll need to come up with, well, we would need to come up with some backup systems there. We'll need some emergency kit storage if we have, so some of the tools are going to be too heavy to move. Yeah, the counterweight could, yeah, we'll need to figure out how to do the counterweight if the winch fails. And figure out if we're on other missions, what other stuff could break if we're on other missions.
Does anyone have any questions for us?
I have a few, but other people can go first if they want.
Looks like it's just you and Dr. Hanachi.
Okay, I have a few questions, I guess, of things I think you touched on a little bit, but maybe you can elaborate on. Are there concerns, and I think you talked a little bit about a hammer test on your initial prototype. Are there concerns with if the weight is off center on the platform? So say you've got one crew member riding up and down, sitting next to a cart of tools, and so the center of mass is skewed one side or the other. Have you looked at that?
Kylie, do you want to take that one?
Yeah, that was the main focus of the testing of the 1/10 scale of the top hat. Just by having cables that cross and make like an X on the long sides, as seen here, that was able to reduce almost all of the translation. And as you can see in the first image there, that's without it, and that's basically exactly what you were expecting, that having the load offset to one side was going to drastically affect the levelness of the platform. And with this system, as again, because it was just testing and figuring out how things were going to work, it does end up cutting off access, and so the next phase is figuring out different cable configurations to maintain that stability, but then also allow astronauts and loads to actually go onto it.
Yeah,
Okay.
yeah, go ahead, Sarah. I'll ask after you.
But go ahead, because I had a related but tangential question. So go ahead.
Actually, related to that, I would like to see, like if you have, if you can take a recording of the testing, that can give us an idea of how you do it, and I kind of would like to, like, you know, I would like to see different scenarios and how things go, and like see the stability that's translated with the improvement that you made. Also, I know it's very hard to, like I'm glad that you took pictures, and because I saw this before, I think I can tell that there is a string and I know where they are. But if you, when you're like recording the video, if you can use different colors of the string, or just make it a little bit easier to,
Yeah.
that'd be great. Yeah.
For sure.
Yeah, and so I guess my related tangential question is, can you flip back to the slide where that shows the platform and kind of the all the cross beams and railings and stuff around it? It looked like, is it open on one side? Yep.
Let's see which one. So this one?
Yeah, that's the one I was thinking of. So let's see. So the side closest to the vehicle is which side?
The
I
one
guess I'm
with
trying to
the-
figure out how the crew gets on and off of this thing if kind of three sides are enclosed and one side is open.
So they would enter the chamber, get on the platform, and then once the platform is on the surface, they would go out the same direction.
The bar that you see there this is actually on top. Like it doesn't go down with the platform. This is the portion that is going to be stationary at the top. Yeah.
That's the chamber at top. Okay. So
Yeah.
where's the figure of the platform that lowers and raises?
This guy. We're still looking into a mechanism that the astronauts can link their harnesses onto. So we'll have another safety bar there. The image that we were just looking at, I think I passed it already. This is actually still probably a better rendition of what we've got so far. But we'll have some sort of like bar or something that they can link onto. It'll be pretty open on most sides with perhaps a cable running around.
We were also
Okay.
looking at having their links come from the top at itself.
Like
And they
an
would link
umbilical
onto it there.
cord.
Yeah, I think it's a key thing to communicate a little stronger than you have as kind of the con ops or the ops con for this. And so pictures that show here's the configuration as the crew's getting out of the lander into this thing. Here's the configuration going down. Here's the configuration on the ground where they egress off of it would help a lot to visualize a little clearer in this presentation. Because if I look at this, so it looks like you would have cabling kind of on two sides and your cross beams in the back, and the front is totally open, or I'm having a hard time visualizing, I guess, in those various phases, what it looks like.
Should be.
I think I'm sure you've thought it through, but just try to communicate it a little clearer.
Absolutely. And we can make some assemblies that show everything integrated together as well. And
Yeah, even a hand sketch would go a long way.
all right.
Yeah, this guy.
Yeah, there you go. That's okay. Let's look at this for a second. So there's your platform. There's your kind of cabling in the corner with your top hat. Then you're picturing a tether of some sort. So and then if you were to take up and down tool carts or boxes of rocks or something, think about how that would be stabilized on the thing and attached. So there's no risk of it rolling off or falling off or anything like that.
At the moment, what we've looked for in terms of carts is that they can set into the holes. If they have legs, they can set into the holes in the platform, which would be large enough for that. However, we are also considering other alternatives, including latches that we will be delving more into in some future work.
Okay, yeah, because we're envisioning having for all the Artemis missions some sort of rolling, I can't tell you exactly what it looks like, but some sort of rolling cart that the crew can pull. And so I could see it being convenient for them to load that thing on this platform and bring it up and down to unload it. So just make sure you can accommodate a variety of different things like that.
You have a good point about demonstrating the different configurations, so we will include that in our final presentation.
Are there any more questions?
Yeah,
Do you have an estimate? Oh, sorry, a total system mass for the kind of what's pictured here for the whole system?
What we have pictured here, we have a pretty good idea of the mass of the platform, top hat, and guide. We're not entirely sure on the chamber yet. So excluding that, it comes out to around 20 kilograms for the platform, around 20 for the top hat as well. And the guide should be around, was it 15?
15. That's a
15.
very high estimate, but yeah.
Which, yeah, our estimate is a little on the high side right now to be safe. And as we finish some more optimization, we'll have lower numbers and we'll have an estimate for the chamber.
Okay, thanks. Yeah, lower is obviously better from a cost perspective to get it to space, but your estimate sounds fairly low to me right now, so that's good.
Is there a mass that we should aim for?
Well, no, not really, other than lower is better. And, you know, if you were doing this as an official, you know, kind of part of the vehicle, yeah, you'd be given a mass allocation. I don't want to give you one, so that's not fair, but, you know, I think the ballpark you're in is very reasonable.
Professor Hanachi, did you have a question for us?
Yes, thank you. So you mentioned, I think Collins mentioned some safety values, and that you managed to, if you can go back to that slide, please. Yeah, what's the highest in the next slide? So what's the highest value there? Here, yeah.
In this slide,
Yeah.
here we have a standard sort of loading condition where we took advantage of symmetry across both the horizontal and vertical, or X and Y, I guess, because we're looking more down at it, axes. And we have a distributed load on each quarter of it, holding a quarter of the load for this model, which represents 2 feet from 2 people. And this gives us a factor of safety of 7.6, which seems large. However, when considering the worst case scenario as well, we need to be able to accommodate for both worst and standard loading. And here we have a maximum deformation of 7.3 millimeters.
Okay, good. Yeah. Good job, guys. This is, Sarah addressed some of my questions, so.
Yeah, this is really good. I guess my only other question, you kind of talked about your top risks for your future capabilities, or I'd say enhanced capabilities. What are you tracking as your top risks for your baseline capability?
We've got a number of different things that we're considering. We're looking at trying to build in ways to have a backup. Like, well, for one, we've already talked about the ladder. So we want to have a ladder in case something, everything fails, you've still got that manual backup. We want the manual backup for, say, moving the platform with a physical crank if the motor fails. Additionally, that's where like the worm gear system allows us to only move the platform when we want to. We've been talking about other ways that we can like eject systems if, you know, stuff completely fails, and most of them involve, you know, breaking the top half off of the cable, so that way we can just kind of drop the platform and be like, well, bummer, you know.
Maybe share my screen. Jacob, I have it up.
Oh, stop sharing.
Stop sharing, please. Yes. So we have started a document, as you can see here, of the possible failures of the system. Like Jacob said, most of them are detaching the whole system and just basically just using the ladder as our main backup. But we also have, if something such as the guidance fails, we can just, we can't, I think, where is it? The platform failure, top half failure, and cable failure, we would detach to the top half. If there's a gear failure, we would use a manual crank, like Jacob said. We are definitely thinking about what ways we can make sure the whole system is in use, but we also want to make sure that if it doesn't work, we don't want anyone using it.
Okay, good. This is good.
One last question for me. I have so the user interface that you referred to, is that, can you speak more about that, or your plans about it? Yeah, this one. Thank you.
It's pretty simple. It's just a few buttons that will connect or disconnect a circuit from running the power through the motor one way or the other. We just want the astronauts to have a really easy button that's reliable to use, easy to find.
And do you have, so is it an actuator? Did I hear an actuator or just an, like, is that going to be a screen or an actual?
These
Button
would be
or-
like physical buttons that
Physical.
are, you can, ideally you'd be even able to feel them through big bulky space gloves, but
Okay.
something that you can find in and operate in low visibility.
Okay. And I imagine this is something for future work, or is that something that, yeah. Okay.
Yeah, I think the design is simple, which I like. Did you say you can also control it from inside the lander? So if you just wanted to send down rocks or something, but not have a crew actually ride it down?
That would be ideal. Inevitably, there's nothing to stop us from making ground control be able to control this thing either. Just ideally, we would want, a very safe mechanism with all the same backups that you get in a regular industrial setting.
Agree.
Yeah, once this works, I'm sure they can make it more elaborate. The spirits of MVP.
Sarah, you were going to say something?
No, I was just saying is in the spirit of MVP.
Are there any more questions?
Not for me.
No, it's very good.
Thank you. In conclusion, we talked about a problem we found where the ladders are light and simple, but they fail to be sufficiently safe and efficient as the primary method of ascending and descending in tall structures in space environments. For our solution, we are proposing an elevator style apparatus with much higher load capacity than a simple ladder to be lightweight and easy and intuitive to use. Our future work includes some high-level FEA optimization and some different features, such as a trailer for a lunar roving vehicle, tool storage, and reusability. We had some questions today regarding talking about if we looked at off-center loading, which we did, and we have cable orientation as a great way to mitigate that. We were asked about the chamber, which we'll have the open side be where the astronauts load and unload, and the chamber itself will not descend. We will work on getting some better renderings of the system in use at different points to further illustrate that. We'll also include some renderings of how a rolling cart may be able to be loaded and unloaded. Our mass we're asked about, we have a reasonable estimate for our mass. It's a little high right now, and our actual values are lower. We're asked about test recordings. For our future tests, we will be taking recordings of how the test is performed so that we can show the viewers a better idea of what we did. Our safety factors, we had to consider worst case scenario as well as standard loading, and our user interface, we were asked about, we are keeping that nice and simple for ease of use and low visibility with big bulky gloves on. Thank you for watching our presentation. We appreciate all input and everything.
Good job. Good job summarizing also the questions. Collins and everyone, I wonder if you added on the questions addressed, whether you're gonna do the whole either like give a picture of like the whole system together assembled. I know you plan on the 3D printing piece. Okay, fantastic.
Absolutely.
Awesome. Yeah, very professional presentation. Sarah, I don't know if you'd like to add anything or have questions for them.
No, it was very good. I'm impressed with what you've done since we last talked, and yeah, agree. I think just keeping in mind it's always good to help the receiver of this information visualize how it's going to be used at all different phases. But otherwise, yeah, I thought it was very thorough, very well done.
Thank you.
Thank you.
Thank you.
Terrific. Good. That's a good practice. So, yeah, we can conclude the meeting here, and Sarah will keep you on the loop on further progress.
Okay, yeah, thanks.
Super.
Thanks again.
All
Bye,
right,
for
Sarah.
your
Thank you.
time.
Have a great weekend.
Appreciate it.
Thank
Yep, you
you.
too.
Thank you.
Thank you.
Bye.
Bye.
Bye-bye.